Welcome to this review of inductors in DC circuits. This is for Level 3 electrical systems. Firstly, a review of Faraday's laws. Faraday actually had two laws related to electromagnetism and induced voltage. The first one was basically saying that as long as there's a change in magnetic flux, a voltage will be induced. And the second one is the one that we have talked about the most in class, which states the size of the induced voltage is directly proportional to the rate of change of magnetic flux. We can see in this image there is a change in magnetic flux because the magnet is being moved in towards the solenoid, which is inducing a voltage. Lenz's law also relates to inductors. In general, Lenz's law tells us that the direction of the induced voltage will oppose a change in magnetic flux that caused it in the first place. In this diagram, we have a solenoid on the right and we have a magnet moving in towards the solenoid on the left. That moving magnet creates an increase in magnetic flux for the solenoid, and the solenoid has an induced voltage as a result. The induced voltage of the solenoid is in a direction that sets up a north pole at the left end of the solenoid to oppose the magnet that is moving in. This won't stop the magnet from moving in, but it does make it harder to do so. These two laws, Faraday and Lenz's laws, are combined in our first equation on our formula sheet. We can see that we have the induced voltage on the left and it is equal to the rate of change in magnetic flux on the right. That is Faraday's law. And there is a negative sign in there to show that the induced voltage is in the opposite direction or opposes the rate of change in magnetic flux that caused it. It's important to note if you are using this formula or the other one that we see later on that is specific to inductors, if you have multiple loops, you need to multiply your induced voltage for one loop by the number of loops to get the total induced voltage for a solenoid. So, moving on to inductors and applying this information. An inductor is just a solenoid with N turns or loops of wire. We're very familiar with solenoids. We can see in this image that there are lots of different arrangements, but they're still the basic same idea. Inductors have an inductance which has a symbol L and is measured in henries or henries if you're French. And by definition, there's lots of different definitions actually for what inductance is, but probably the easiest one for us is the inductance measures how effective the inductor is at opposing the change in current in the circuit. Changing current in a circuit will cause a change in magnetic flux in the inductor, and that's how that links back to Faraday's law. Now, inductance can be affected by a number of things, but the main ones that you would be expected to know are the number of loops of wire. Higher loops of wire means bigger inductance. If the cross-sectional area of each loop, if that increases, you'll get bigger inductance. And finally, if we add an iron core, that increases inductance as well. We have two different symbols for inductors that might come up. The one on the left doesn't have anything in the middle of it, so that is just a standard inductor with no iron core, and the one on the right is an inductor with an iron core, and that's what those two lines represent. You'll notice the loops on the symbols are slightly different. You could get either of those. They're both recognized symbols for inductors. So here is our second equation for inductors and Faraday's law. Again, we have induced voltage on the left, but instead of rate of change in magnetic flux, it's saying the rate of change in magnetic flux is effectively inductance times the rate and change of current. And once again, we have a negative sign to remind us that the induced voltage across the inductor is going to oppose, in this case, the change in current that causes it in the first place. This change in current will happen when we close the switch in a circuit with a DC power supply or open the switch in the circuit with a DC power supply. When you are doing alternating current stuff with inductors, the current is always changing, so we don't have to worry about switches. When the switch is closed, once the current gets to its constant state, the only thing the inductor does in the circuit is its resistance will affect the circuit a bit in terms of current. But other than that, it doesn't really play a role. So you may be expected to explain what happens in a DC circuit that has an inductor in it when a switch is closed. The key ideas they're looking for is that there is a change in current, as mentioned on the previous slide, in the circuit as soon as the switch is closed, which induces a voltage, as we have already said. And from Lenz's law, this induced voltage opposes that change. All right, that means the voltage will try and stop the current from flowing in the circuit. This means the current will take time to build up instead of instantly going to its maximum point. We can see here on our current time graph, the red line, which goes straight up the vertical axis and then straight across at 8 milliamps, is what would happen if there was no inductor in the circuit and that switch was closed at time equals 0. The curved line, which I think is purple, is showing what actually happens to current when there is an inductor in the circuit. That current builds up more slowly, but eventually gets to its maximum. And once it's at its maximum, that inductor isn't affecting the circuit apart from its resistance. Now, it's really important that we remember that Ohm's law applies here. So we can use Ohm's law to work out what our maximum current in the circuit will be, because the maximum voltage of the circuit will be the supply voltage. That's the maximum voltage that will be across the resistor once the inductor is no longer affecting the circuit. So in the example that I had previously, we had a 10 voltage supply. So once our inductor has no longer opposing the current, the voltage across the resistor will be 10 volts. Then we divide that by its resistance, which in this case was 1.25 kilo ohms, and we get a maximum current of 8 milliamps. This graph is showing what happens to voltage over time when you have got a circuit that has an inductor in it. The green line is what's happening to the voltage across the resistor. Because the voltage across the resistor is directly proportional to the current from Ohm's law, you should see that it follows the same sort of pattern as our previous graph. But the voltage across the inductor is actually biggest at the beginning, and that's because that's when the change in current is happening the quickest. So we have a maximum induced voltage. It cannot be any bigger than 10 because that's our supply voltage and Kirchhoff's laws apply. As that voltage across the inductor drops, the voltage across the resistor will increase so that the total voltage of the two of them will always be 10 volts. And that's the application of Kirchhoff's law. If you get an inductor in DC circuit question in the exam, one of the things you're often asked is about the time constant. The time constant is the time for voltage or current to change by 63%. This is the same definition as you have for capacitors as well, but the equation is slightly different. It's the inductance divided by the resistance. In our example circuit back on slide 7, that works out to be 0.16 milliseconds, so quite a short time in this case. So one time constant is the time for voltage or current to change by 63%. Now it's really important that you know what your curve is doing when you're trying to work out how to apply this. If you have got a decreasing curve, like the voltage across the inductor that we had in the previous slide, okay, the 0.16 is the time for the voltage to drop to 37%. That is a change of 63%. For values that are increasing, like current or the voltage across the resistor, 0.16 milliseconds, one time constant, is the time for that current to go from 0 up to 63% of its maximum. Here are a couple of examples. So the first example is when we have the decreasing curve. This is the voltage across the inductor. Now I want to draw your attention to the equation in bold on your right, which says V equals 0.37 n to the power of n times V max. So if you want to work out the voltage after one time constant, that little n will become 1. If you want to work out the value of the voltage after two time constants, where we've got the n, that will become a 2. So for example, at two time constants, if you want to find the voltage, it's 0.37 squared times 10, the maximum voltage for our circuit, and we get a voltage of 1.37 volts. Because that's at two time constants, we have to double the time, and we could plot those points on our graph. So at 0.32 milliseconds, if I plot an X, I will see on my curve that that works out to be about 1.4 volts. Here we are with our second example, and this time we are looking at the current build-up in the circuit when the switch is closed. We can see that we have got a formula on the right. This one is our current is equal to bracket 1 minus 0.37 to the power n, where n is the number of time constants, times I max. So if we look at the bottom example, at 3 time constants, the time would be 3 times 0.16 milliseconds, which gives us a total of 0.48 milliseconds. At that time, the current is 1 minus 0.37 to the power of 3 times 8 milliseconds. That gives us 7.6 milliamps. Just like everything else we do, we have our law of energy conservation that also applies to inductors in DC circuits. This law of energy conservation is looking at the energy, of course, not changing in total, but just changing forms. So in this case, our energy supplied by our power pack or battery is going to be equal to the energy used by the circuit components. Now in this case, half the energy is actually stored in the inductor's magnetic field, and the other half of the energy is turned into heat by the resistance of the circuit. The energy in the inductor can be calculated using E equals a half L for inductance times I squared. That's the current squared. Right, so what happens when we open the switch? Now we have got an open circuit. Kirchhoff's voltage law only applies when we have got a closed loop. So we are not bound by Kirchhoff's voltage law anymore. That current, when you open the switch, is going to drop to 0 pretty much instantaneously. That means your change in current, or rate of change in current, is very, very high. Now, induced voltage is directly proportional to that rate of change of current, so it will also be very, very high. This induced voltage, remember, opposes the change that tried to cause it in the first place. So it is trying to stop the current from stopping. And what happens is all the energy that was stored in the magnetic field is released as a really big spark that jumps across the open switch. And that spark can damage circuit components. Well, that covers it for inductors in DC, our review for the exam. Thanks for listening all the way to the end. If you got it this far, I really encourage you now to go away and maybe make a smaller or shorter version of this notes, so you're actually actively getting your brain engaging with the information and then trying to apply it to some exam questions.